I not been recording all this time? Yes, I have not. So yeah, just to roll back the tape. So we've just calculated that we had a cop car chasing a thief's car, but what happens to the thief's car is that it collides into a truck moving in the opposite direction, and because maybe the truck is heavier, its momentum is larger, or for some reason or another its momentum is larger than that of the car. So after the collision, they end up traveling together in the opposite direction. Now the second part, and then we find out that they travel together at 10 meters per second. Now in the second part of the problem, we're told that research shows that the force required for a collision to be fatal is 85,000 newtons, right? Now Newton is the unit that we use to measure force. So the force units are Newton. These are named after Sir Isaac Newton. And how we express it, it's mass times acceleration. So it's kilograms times meters per second squared. Right? So these are the units for force, and this equals Newton. So 85,000 kilograms meters per second squared need to be applied during a collision to cause fatal injuries. And this collision lasted for 0.5 seconds. So we must determine by means of a calculation whether the collision could result in a fatal collision. So what we know is that the resultant force from our impulse equation, the resultant force is the change in momentum divided by the change in time. And we also know that after the collision, these two are added up together. They're the same thing. They're the same thing now, right? Oh, no. I'm getting it wrong. Okay. All right, so the resulting force is delta P over delta T. However, we also know that the resulting force is also times the change in time is also the change in momentum. So we can work out the change in momentum for the car and for the truck in both cases. And we will see how we come to a conclusion. Are we still on Jamboard?
Yes.
Okay, cool. And on the learning guide, we're on page 60. On page 60. Right, so we know that the change in momentum is we know the final velocity of the car, of the thief, and we also know the initial velocity of the thief's car, right? The final velocity is negative 10 meters per second. We've calculated that. And its initial velocity is 40 meters per second. That was given. Right, so we'll just keep that in mind for now. And we're going to use that to work out for the car. The change in momentum is the car's mass times the change in velocity, which is the mass in kilograms times V final is negative 10 meters per second and this subtracts 40 meters per second, and this equals the resulting force. We don't know if this collision had a force that could cause fatal accidents or injuries, but we know that it lasted for 0.5 seconds. Now on the right hand side we have 1,000 kilograms times negative 50 meters per second equals 0.5 seconds times resultant force. When we divide both sides by 0.5 seconds, then we have that divided by 0.5 and that divided by 0.5 seconds. And remember, the units for a force are kilogram meters per second squared. So we're going to show how we go from these units jar momentum, which is kilogram meters per second, and after we divide by time, we get F res, resulting force, in kilogram meters per second squared. So I'm going to show how we do that, right? So let's first divide the numbers out. We have 1,000 times negative 50. That should give us negative 500,000, negative 50,000. Yes, negative 50,000 kilo. Let me not put the kilograms. My arithmetic is not so great. And then we divide that by 0.5. So we've got, I just want to do this, kilogram meters per second divide by second. So then this becomes kilogram meters per second times 1 over s, and this gives you kilogram meters per second squared, which is kilograms meters per second squared, like that. And if we divide negative 50,000 by 0.5, how much do we get? I think we get more than 100,000. Yeah, we're dividing.
With 50, 0.5.
Yeah, so we get 100,000. Kilogram meters per second squared. Newton. So we get a net force of 100,000 Newton. So the negative simply tells us that it's in this direction. So it's 100,000 Newton west, acting towards the left, and this is greater than the 85,000 that we're told can cause fatal injuries. So if the force that we calculate that the car experiences after the collision is greater than that which research says it can cause fatal injuries, is this collision fatal or not? Yeah, the thief died, so the cop just had to report that. And we can do the same calculation for the truck. So I want you to challenge yourself. Wait, are you still quitting after this class?
Yeah.
Okay, because I was gonna suggest challenge yourself by working out the other methods of working it out. So they work it out for the truck if we assume to the right is positive, and they also do it for the truck and the car if we assume that to the left is positive. And it's also done with other formulae, just to show how many different ways you can get to the answer for this type of problem. Okay, and then there's a whole discussion of impulse, and then it also talks about crumple zones. I think we talked a little bit about that. And then there's a chapter summary, and from that we have a couple of word problems for momentum that we can work out. Yeah, okay. All right, but just an overview of the chapter summary. There's two types of laws that are at play that are by Isaac Newton. So it's Newton's second law, which is that a resulting force acting on a body will cause that body to accelerate, and that is just illustrated by force multiplied by force equals mass times acceleration. And then there's also Newton's third law. This is on page 65. And it's a simple action versus reaction law. It's basically saying for every action, there's an equal but opposite reaction. So there's always a pushback whenever two things interact. And then we have the conservation of momentum law. And it's that the momentum of a system the momentum is rather the mass times the velocity of the object. And then there's a system of momentum of a system, which is like if you're considering one object that's moving, it's just the mass of the object times its velocity. And if it's two objects moving towards each other, you consider the momentum of the two objects etc. Just did a little sequence there to show that if you add the momenta, you get the momentum of a system. And then we also have conservation of linear momentum. So the conservation is that the momentum before equals the momentum after for a system. And this is the mass of object 1 times the initial velocity of object 1 plus mass of object 2 times initial velocity of object 2 plus any other objects in the system. And that equals the momentum of the second momentum or the final momentum of object 1 plus the final momentum of object 2 and so forth. So this just also illustrates how the same way of thinking for sequences and series can also be applied here. But just so we can explain conservation of linear momentum. And then we also have elastic versus inelastic collisions. So elastic versus inelastic collisions. Elastic conservations, the momentum is conserved and the kinetic energy is conserved. So P and kinetic energy are conserved. But for inelastic, only the momentum is conserved. The kinetic energy changes. Remember that thing we talked about when a crater is formed on a moon, the rock that falls on the surface of the moon changes to molten rock, so it changes form. So the kinetic energy is not conserved because it converts to heat energy to melt the rock into molten form, and that's where the kinetic energy goes. And then we also have impulse, which is the product of the net force times how fast, how long it takes rather the force to be applied. It can be in a collision, etc., and that also equals the change in momentum. And yeah, the applied resultant force acting on an object equals to, and then from this equation we can also get that the applied net force is the same as the change in momentum over the change in time, and the impulse is also equal to the change in momentum. So that pretty much sums up this chapter. And then from it we are going to move to vertical projectile motion in one dimension. So what this chapter just means, okay, I just want to share this one so that we start a new chapter on a new jam. Okay, close this jam. So yeah, the next chapter we're going to discuss is it's about when you throw an object into the air. When you throw an object into the air, and assuming that it travels vertically up, we're going to do calculations of that type of motion as the object is in the air, or rather travels up and then back down. So we're going to work out how fast it moves, how long it takes, and how high it moves. And in each of these cases, all of the problems, the objects are subjected to acceleration due to gravity. So that's always acting. So I'll just say 1D vertical projectile motion. And then that, I should just say Saturday.
You started writing.
No, I'm just typing out the name onto the Jamboard. The name of the... Okay, I'm presenting my screen. Okay, and for this one, we are At this stage, we're expected to know units and unit conversions. So that's from grade 10 science skills. Rectilinear motion, so movement in one dimension, but that's like horizontal. So to the left, to the right. Could be a cart moving sideways, it could be a car, could be a ball rolling sideways, etc. We're also expected to know linear equations from grade 10 and equations and inequalities, as well as quadratic equations, and all of this stuff is from grade 10. But in the previous grades, the motion of objects in free fall would always be subjected to acceleration due to gravity, right? So in 1D vertical motion, objects that are either, let's say you throw a ball up. Let me use that doodle thing instead. Yeah. So let's say you're throwing a ball up. And this ball is being thrown up into the air, right? That ball is thrown up. Right, so the ball is being thrown up. At some point, the ball will be somewhere here. Right? And at that point, it stops moving for a moment. Just a very brief moment. Its velocity is 0. Its velocity is 0. And then it comes back down. Now, the dynamics for when it's coming back down are not necessarily the same as its dynamics for when it's coming back, when it's being thrown up. Right, so this just shows us, like if someone is throwing up a ball, let me draw. Yeah, there's a guy throwing a ball up in the air. So let's say a ball is thrown up like that, right? Our guy throws the ball up, but that's actually Warrior 1 from yoga, but okay. So our guy is throwing the ball up like this. Now after it goes, it carries some speed with it, it picks up some speed, some momentum. And then after it does that, it then hits a certain peak. Now at that peak, it stops moving. It stops speeding, and then it changes direction. After some time, it changes direction, right? Now after it changes direction, it then starts to fall down to the floor, back to the floor. And as it's falling, because all objects that are falling are subjected to acceleration due to gravity, right? So gravitational acceleration is the rate at which every body on the planet accelerates towards the center of the earth. And that's called gravitational acceleration, and it's a constant estimated at about 9.8 meters per second squared. So always use more or less that figure to calculate problems of this nature. Yeah. So when an object is moving upward, it's still subject to the gravitational acceleration, even though it may have a velocity that's moving it upward like that. And just as with left and right problems, you can choose your own convention such that you can take upwards as positive, then the resultant is negative as positive, or you can take downwards as positive, then the opposite is negative. So in this case as well, if you take up as positive, then down is negative, and likewise if you take up as negative, then down is also positive. So they work almost the same. So if you choose upwards as your positive for your convention, then the opposite is the opposite sign. The opposite direction is the opposite sign. So if you, for example, choose downward as positive, then your acceleration due to gravity would be positive. And if you change the convention, or rather you start with the convention as upwards is positive, then your acceleration due to gravity is negative. Then the second thing is there's a time component. So to travel up, there's a certain amount of time that the object takes. So from when it's thrown, which is there, where it starts being thrown, to when it reaches the top, where it stops moving, before it comes back down. There's a certain amount of time that passes, and that time is important. Because in a lot of cases, the time going up would be the same as the time traveling down. Right? So when you look at the time on a scale, so for the upward movement, then you'll have change in time. Then for the downward movement, you'll have twice the change in time. And that just shows you that between a certain point when the ball is mid-air and when it stops in mid-air and then comes back down, the time going up and the time going down are the same, the change in time. So that's what's illustrated on page 73. There's an experiment from pages 73 to 76, but right after that, revision is called upon for the equations of motion in one dimension. And it's that your final velocity equals initial velocity, and this is on page 77, plus acceleration times change in time, right? And I'm using the acceleration due to gravity simply to illustrate that we are moving in the vertical direction. And then instead of x, I'll use for the next equation change in y, because we know that vertical axis is y and horizontal axis is x. So if it were change in x, it will just simply show us that the motion is in this perspective of movement, but since it's x and y, it's in the y direction, then it simply tells us it's in the vertical direction of movement. So delta y becomes initial velocity or final velocity plus initial velocity. All of this is over 2 times the time. And these are the equations we're going to use to solve a lot of the problems in here. Again, delta y is then initial velocity times the time plus a half times the acceleration times the change in time. So I'll just put change in time there. And lastly, we've got another equation, which is the v final is squared, and it equals the initial velocity squared plus 2 times the acceleration due to gravity multiplied by the change in vertical displacement. So just to explain the terms, Vf is v final, Vi is initial velocity, change in displacement is delta y, so change in vertical displacement is delta y. Delta t is change in time, and we have acceleration due to gravity vector. And that's always a value of 9.8 meters per second squared. Alright. Yeah, so change in position is your delta y. So if you so that part that says important just tells you about choosing a convention. So you must just remember that the displacement and the final position are not the same. But you can just read through that. Sorry. Alright, so we're gonna do our first example, which is projectile motion. And we're told that a ball is thrown vertically. This is on page 78.
Stop.
Okay.
No, not you, sorry.
Oh, okay.
Sorry, please.
But everything is clear on the Jamboard, right?
Okay. I'm on the projectile motion.
Yeah, that's page 77, 78 of the textbook, right? So we're told
Yes.
that someone is throwing a ball up in the air, right? So we've got a person throwing a ball up in the air, and that ball is way up in the air, right? And it's moving at a certain velocity. We're told that that initial velocity is 10 meters per second. So when it leaves the hand of the thrower, it leaves at, we'll choose upwards as negative because our G is 9.8 going down, and that will be so that our G is positive. Alright? Then in the picture, we're told that the ball is at a height of 1.5 meters above the person throwing it, the point of release, right? Now we have to find exactly how high the ball goes in mid-air, and that's going to be the maximum height that the ball reaches before it changes direction. Right? So we want to find the maximum height. Like how the highest it can go from when it's thrown to, from when it's thrown. The highest that it can go from when it's thrown, right? So the discussion is that we're required to determine the maximum height the ball reaches and how long it takes to reach that height. And how long it takes to reach that height. Right, so we've at least tried to look at some of the things that are required of us. We know that at the top, the thing has a velocity of 0. Because in our earlier discussion, at this point where the ball changes direction and stops going upward and starts going downward, so I'll just do that to show that it changes direction. Right, so at this point at the top, where it reaches its maximum height, it stops going up and it starts traveling down. That's where the final velocity is 0. And we know that initially its velocity was 10 meters per second or negative 10 meters per second because upwards is negative. Then we can now use one of the equations we just described above from grade 10 or 11, which is that the final velocity squared must equal the initial velocity squared plus twice the acceleration due to gravity vector times the change in vertical displacement. Now we know that the final velocity is 0, which is at the top, and the initial velocity was negative 10 meters per second, which is the velocity at which it started traveling. This you square it, and then you add it to twice the acceleration due to gravity vector, and we don't know the change in vertical displacement. So then we have 0 equals 100 plus 19.6 times delta y. Then we have 100, negative 100 equals 19.6 delta y. And then if you divide right through by 19.6, you get negative 5.102 meters. So what that just tells you is that since we started by assuming that going upwards is negative, then the ball has to travel negative 5 meters above, and that's the maximum height it reaches. So it reaches a height of 5.102 meters above the point at which it is thrown from the person throwing it. Now to answer the second part, which is how long does it take to reach that height of 5.1 meters? We can use another one of those equations. And we can simply use V final equals V initial plus acceleration due to gravity times change in time. Final velocity is 0 because that's in the direction going up, that's the final velocity vector that's recorded. It's 0 where it changes direction. Initial velocity is negative 10, and we add that to 9.8 multiplied by delta t. That gives us negative 10 equals 9.8 times delta t, and delta t equals 10 divided by 9.8 seconds, which is 1.02 seconds. And that's just how long it takes for the ball to travel a distance of 5.102 meters above the head of the person who threw it first. And this is before it starts making its descent. It's traveling down. So far we're together. Wait, am I still screen sharing? The call ended. I thought there was an alert. Ah man, after an hour, man. Okay, let's do this. This one has. Okay, I'll just give her a heads up to just join the same meeting. I'll just share the screen. Ready to join? Yes, we are ready to join. I'll just tag her here. Oh man.
You were talking to yourself.
For the longest time, you know that. For the
How
longest
long
time.
was it?
Probably a few minutes. Maybe 5. 5, that's a long time still.
I feel
So,
like a lot of successive days.
I know, right? Hey, let's add people. Joy. Monsa. Alright. Still using the same Jamboard. I got you. Let me just do this.
She's the one that's in.
Yeah, she's writing it on the other end.
Thank you. Help. It's so shame.
Use the invite and just send.
She's back.
Yeah, she's back. Guess who's back?
No, it's fine.
Back again. I'm gonna share screen again. Where did I lose you?
We said, I was asking a question actually to say we're not factoring in the distance between the person and the ball in calculating the change. And I don't know what you said.
The change in time.
Yeah, so, yeah. She said, I don't know if I was myself.
Where? Which part? Use a different color so I see where you are.
So the gravitational acceleration part times the change in time, that's where I wrote over.
Oh, this part here. Let me just mark it in yellow. You mean this part here?
Yeah.
Okay.
So that's really lost me.
Yeah, so here we don't need to factor in the displacement because the formula itself does not have space for it, 1. 2, we've also just calculated it before. So we know how high the ball goes above the head of the thrower, the person throwing it. So since we know the initial velocity at which it started moving, as well as the final velocity where it's 0 when it changes direction from traveling up to traveling down, since we know those two velocities and we've got a standard 9.8 meters per second squared for acceleration due to gravity, we can just substitute those that we know with the correct signs. Of course, this one is negative, and then we just fill that in, and then after substituting we'll be able to work out we'll be able to work out the change in time. So the change in time is simply what we get after we play around with this equation here. We solve for this equation here. So once we solve for that equation, this equation here, or rather this one, so after solving for it, we know that it's negative 10 meters per second because up is negative, and we know V final is 0 meters per second, and we know this is positive 9.8 meters per second squared. So we just substitute, then we solve, then we get that, and that's our final answer. So yes, no need to use the displacement for that equation.
Okay.
Yeah, there's no need. Then we have to do something else here. We must determine the time or times when the ball will be at the position shown in the photograph. So what do we know about that position of the ball being shown in the photograph? What do we know about the ball being at this position here? What do we know about the ball being at this position here?
We know that it took it a second, 1 minute and 2 seconds to get there.
It traveled 1.02 seconds to go from the hands of the thrower to the highest point, which is 5.102 meters in 1.02 seconds. This is the information we get from these two answers. So to travel a maximum height from the thrower to the topmost position where it changes direction, that's 5 meters in just over 1 second.
Yeah.
So now we need to find at what time will this ball travel to the height that's shown in the picture. And the height that's shown in the picture on the doodle here is what I've circled in red. So this here is the height it takes, is the height to get to 1.5 meters. So we need to find how long it takes to travel that height. So my question initially was, what do we know about the information in the picture, which is the one that's circled there? How high has the ball moved in that photo? What do we know about that photo?
It went 5.12 meters at 1.202 seconds.
Not really. That's not what I'm asking. What I'm asking is, in the picture, the ball is not at the maximum height. Remember, we're told that a photograph is taken when the ball is 1.5 meters above the point of release. So at 1.5 meters above the point of release, that's when, that's what's shown in the image. So what I'm just asking is, how high is the ball from the hands of the thrower in the picture? Because we need to find, it's 1.5 meters, yes. Because now what the question wants us to do is to find when the height is 1.5 meters, what is the time? And the reason for that is because we know that the ball travels upwards first, right? And it travels your 5.102 meters, and then it changes direction and travels down. But we know that somewhere there it's at 1.5 meters, and it will be at 1.5 meters again on its descent. So what the question actually wants is there are two times, right? The first time is when it's at 1.5 meters going up. So at 1.5 meters going up, and a second time at 1.5 meters from the thrower, above the thrower, traveling down, going down, right? So now we are going to go back to our maths class. We know that we've got a change in displacement, which is 1.5 meters, and it also equals initial velocity times change in time plus a half times acceleration vector times the change in time squared. And we can write this as a quadratic equation. So we can say 0 equals a half g delta t squared plus v I delta t minus delta y. So now it's minus delta y because, let me just erase this out and write it afresh. So we're going to have delta y minus delta y equals negative delta y plus v initial delta t plus a half g delta t squared. This gives us 0. That equals 1 over 2 g delta t squared plus vi delta t minus delta y. And that's the same as, I guess, in the learning guide, 1 over 2g delta t squared plus vi delta t minus delta y equals 0. So it's one and the same thing. It's just writing one on the other side of the equation. Now, if we substitute, we don't have a value for delta t. So we don't know the times for the thing going up or down at 1.5 meters. But we do know the value of the acceleration due to gravity. We also know the initial velocity, which is negative 10 meters per second. And we also know the displacement is negative, or rather just say 1.5 meters. And if we look at this equation, I'll just use a green color. We've got an equation, yeah?
Sorry, I've been refreshing quite a bit.
Okay.
Can you just, I don't know, refresh or something so it can show?
Okay, I'm also sharing our screen, eh?
You are, but it's only showing page 3.
Okay, try refreshing. Because I just switched the screen on the jam and then it opened a new page. Okay, have you joined now?
Sorry?
Were you able to join now?
I'm here, but it's still, we're seeing the same thing, but I think it's delayed. You can continue.
Okay. I just refreshed on my window here.
There we go.
Yeah, still there's such a big lag. Wow. So, going back to our earlier grades in math, we're going to borrow from math a bit. And we're going to borrow the quadratic equation, right? So, quadratic equation remember when we did that example on factorize last night, and I showed you that some functions, some expressions rather, you can factorize and get like an x plus a number in a bracket times an x plus a number in another bracket. Remember that one? So sometimes you can't factorize quadratic expressions and you have to use a quadratic equation. So this equation that's circled in blue, the one that's written in green, it's called a quadratic equation, right? We're going to borrow from it and we're going to substitute these values of A, B, and C as if we are using quadratic equation, right? And we're going to get two answers for it. They're not going to be natural numbers, but they're going to be real numbers, that's for sure. They might not necessarily be rational either. But when we use this equation, we substitute as follows. So we say our equation is first a half times 9.8 times delta t squared. We don't know the time, but we know we're going to get two answers, two possible answers, because the delta t is raised to the power 2 plus initial velocity is negative 10 times delta t minus our change in displacement is 1.5 meters. That equals 0. So now we have 4.5 plus 0.4, so it's 4.9 times delta t squared minus 10 times delta t minus 1.5 equals 0. So from this, in our quadratic equation, this here becomes A, this here becomes B, and this here becomes C. And now we're going to substitute each of these into that equation, and we're going to get the possible answers for we're going to get the possible answers for t, for delta t. So I just want to write the equation down proper. So we have 4.9 delta t squared minus 10 delta t minus 1.5 is 0, and we're using minus b plus delta b squared minus 4ac over 2a, and we also have minus b minus b squared minus 4ac, all this over 2a. And these are the possible answers for delta t, right? And how we're going to solve them, I couldn't remember on this slide, our A, this is A, 4.9 in green at the bottom there, B is negative 10, and C is negative 1.5. So we're going to now substitute as follows on the next slide, right? So if we take negative b, that's negative times negative 10, plus b squared is negative 10 squared minus 4, a is 4.9, and c is 1.5. All of this is over 2 times 4.9. On the other side, we've got negative into negative 10 plus negative 10 squared minus 4 into 4.9 times negative 1.5. All this is over 2 times 4.9. Then we have 10 plus, I guess, the square root of 70.6. If you work that out with a calculator, equals 9.8, and also 10 minus square root of 70.6 over 9.8. Then this should give us 1.02041 plus or minus 0.857386. And this part here is especially important because the plus or minus just simply shows us that we can have 1.02041 plus 0.857386, or we can have 1.02 minus 0.857, and that gives us that delta t is 0.16 seconds, or delta t is 1.88 seconds. Right. Now, this should be the other way, but it's fine. Should be 1.88 seconds or 0.16 seconds. Now, remember the time it takes to travel up. The time it takes to travel up, right? T traveling up to wave velocity 0 took to H max, which is 5.102 meters. It took about 1.02 seconds. Remember that. But now, if we subtract 0.8573 seconds from that time to travel to H max, if we subtract the 0.8, which we're shaving off a little bit of time, so from the 5.102 meters travel time, which is 1.02 seconds, if we subtract 0.857 seconds, right, then we will shave off and we'll have enough time that leaves us with how much time it takes to travel 1.5 meters on the way down. And that's what this answer is here. And in the same breath, if it's going to take us 1.02 seconds, if it's going to take us 1.02 seconds to travel 0.16 meters above, then it would take 0.16 seconds to travel from the release to the first 1.5 meters. That's 0.16 seconds. Now, after traveling a total time of 1.02 seconds to the top, if we add 0.857 seconds to that travel time, then we get this amount, which is 1.88 seconds. And in 1.88 seconds, the ball will be back at 1.5 meters above. So in other words, how this ball travels, it travels 0.16 seconds to a height of 1.5 meters. And then it travels a total time of 1.02 seconds right up to where it stops traveling at a certain velocity to v0. Now, after changing direction and it travels down, if we add 0.857 seconds, which is where the time it'll take for the ball to be back at 1.5 meters per second. So we add 0.857 seconds. Then it would have traveled a time of 1.88 seconds to be back at 1.5 meters above the thrower's hands. So that's what the 2 times mean. So in other words, the maximum height the ball reaches is 5.102 meters, which is what answer 1 was requiring. Then the second answer was, how long will it take to reach 5.1 meters? That's 1.02 seconds. And describing the whole motion of the ball, when the ball leaves the hands of the thrower at 10 meters per second, it travels 1.5 meters in 0.16 seconds on the way up. And then after traveling 1.02 seconds to the top of its motion, to the peak of its motion, and then changes direction, it travels 1.88 seconds to be back at 1.5 meters above the hands of the thrower. So that's just the long and short of us describing the motion of the ball according to these timestamps here. So traveling up, it goes up 0.16 seconds to 1.5 meters, then travels the full height to 5.1 meters in 1.02 seconds. Then to go back to 1.5 meters, it travels 1.88 seconds. I'm genuinely feeling tired now. So I'd like us to stop here for the day. And with that, I'm gonna stop recording. So wait, Nobutle.
Yeah.
So since you're canceling class today, that's fine. Would you mind sending me then email to that effect?
That I'm quitting.
Yeah.
No.
She's joking.
Okay.
She was joking.
Oh, okay. That's fine. Then we'll stop here today. But please go through the discussions in the textbook there, in the learning guide. And then try and do the problems in the worked examples. They're usually step by step and they explain the concepts anyway. So just revisiting the concept and attempting the problem should do. But like I keep saying, just send me a shout if you need some advice or whatever. Don't rely solely on our classes. Apply a little bit of pressure on your end as well. And I'll also